Let's look at the next stage in terms of Taylor polynomials and their remainders. That's a quadratic approximation. So we've got a function, we've got our linear approximation. T1 is f of a plus f prime of a times x minus a. And we don't want to throw away that work. There's no reason to. It's already a pretty good approximation. We just want to add something to it that won't screw up what's good about it already, but will make it better. And so we're hoping to get something like this pink curve that, allowing it to curve as a quadratic can, might make it match this function better. So we really want to go back and say, what's good? What's so great about T1? Why do we call that the linear approximation, or the best linear approximation? And the key is that T1 of A, this dies, you just get f of a. That's just that it actually goes through that point. Okay, that's would be pretty bad if it didn't do that. But the other thing is that T1 prime of a, its slope, the slope of that straight line, well, that's just the derivative of this linear function. That's where this dies. This is a constant. Remember, once you fixed a, that's a constant, times the derivative of x minus a, that's 1, so you just get f prime of a. That's just another way of saying, yes, it really is the tangent line. The slope of this function, that happens to be linear, is at a the slope of the arbitrary function that you're trying to approximate. Well, what if we could get something where we still had those properties, we added some quadratic term to make it T2, and we're going to hope that we can still have T2 of a go through the right point with the right slope. And what if we could match the second derivative at that point? Okay, well, what would we have to add? First, let's see what we'd have to add to not screw these things up. We certainly need to add some sort of quadratic term that is 0 at a. Okay, that's easy. Okay. And it should have 0 slope at a. So the quadratic piece that we're adding in here should be like this. Something that looks like, that has its vertex at a comma 0. And we're going to add that in to the blue to make the pink, hopefully. Okay, well, there's only one kind of function that can do that. It's some mystery constant. Let's see if I can squeeze it in here. I'm going to move the y there. Times x minus a squared. That's what an arbitrary parabola or quadratic function that has vertex a comma 0 is going to look like. The only thing we actually get to choose and have both of these be true is this constant c. And we're going to choose the constant c to make the second derivatives come out right. This is, if you get this part, this is really the key, I think, or one of the big keys and you can even maybe start to guess roughly how the story is going to go after this, of like maybe we do a cubic or a quartic, a fourth degree or whatever. We're going to keep adding some interesting constants times x minus a to a power. And it's going to not screw up what's already been good and then make it even better. So let's see what c has to be. Okay, so f double prime of a, we're assuming, is something we've calculated and hopefully is easy to calculate. Remember, that's that idea of the base point being easy. And we can just calculate T2 double prime. A constant has already died at the first derivative level. A linear function, that dies at the second derivative level. And the second derivative of this, you're just going to get, let's see, T2 prime of a. Okay, well, let's leave that in there just for now. It's the constant f prime of a plus 2c x minus a, but really we're interested in T2 double prime of a. Oh, sorry, that's of x, my bad. That's a general x. T2 double prime of x, that's where this dies, and you get 2c. Well, it's a constant, so certainly that's T2 double prime of a. So the point is, it's really easy to take the second derivative of a quadratic, and you get a very simple number. But that 2 is important. That's really something that's very important. So we're going to see a 1/2 coming in a second. It's going to be forever in this context from now, and it's simply because the derivative of a quadratic, when you take that derivative the first time, you get a 2 coming down. So, in other words, c has to be, yeah, so I'm going to equate it to this guy, f double prime, and so let's see if I can get my eraser. So we're going to get, let me just erase this part, because I want to save this. We'll get that c is 1/2 f double prime of a. The only way that's going to match is if this magic number, which we already know, has to match the second derivative of t2, and that was a calculation. That's t times our mystery constant. So this is not a mystery anymore. I'm going to cheat a little bit and make those axes really small. And so, in fact, here's our formula. There's the second degree, sometimes called second order. It's really a degree, but sometimes you refer to this as order. I guess because it's using two derivatives, and that's usually where the word order comes in. So the second degree, or the second order, Taylor polynomial, or a polynomial approximation to the function f at a. Let me make a comment that I make all the time when I talk about the linear approximation and the tangent line. A big mistake is in terms of which things are constants, which things are variables. A, you want to think of as a constant. It's often an absolute fixed numerical constant. It's just we want a general formula that doesn't lock us into just one number. But you want to think of that as a number, and f of a is a number that you're going to calculate. And we'll do an explicit example right in just a sec with cosine. F prime of a is a number. A is a number. 1/2 f double prime of a, this coefficient we just figured out, is a number. A is a number here. The only place x's appear are right here and right here. It is a quadratic function. Nothing more complicated. You should not have an f double prime of x or an f prime of x or an f of x in here in particular. That would make this a ridiculously complicated function. The point is that it should be simple. It should be a quadratic. We are trying to reduce an arbitrary function, f, to relatively simple algebra, the kind of stuff we've been doing for years. So let me do y equals cosine x at a equals 0. Just right here at the base point. Okay. So let's just go from the start. And in fact, I could mention there's actually a t0 approximation here. The 0th degree approximation is just the constant. Just take f of a and just don't include any of this stuff. It's just the constant value of your function at the base point. That's always just going to be a horizontal line that goes through your base point. It's usually a pretty bad approximation. In this case, that's going to be 1, because that's just cosine of 0. So that would be saying, I'm going to approximate cosine and saying it's always equal to 1. Not so good. But an interesting thing is that t1 of x, if we want to get t1 of x here, well, let's do the ingredients, okay? We know, we've already calculated that f of a is f of 0. Specifically, that's cosine of 0 is 1. F prime, let's get f prime of x first as a function, but then immediately, and this is where the mistake often gets made, plug in the base point value. This is minus sine x, and so what we really care about is f prime of 0. Oh, minus sine of 0 is 0. Let me just write it out. Okay, well that's because if you look at this picture, this is not only the constant approximation, which is usually a terrible approximation, it's actually equal, it is the tangent line at this point. And so it's not quite as, this wasn't quite as crazy as it would be in a lot of cases. Like here, the constant approximation would just be horrible. It'd be like this. It doesn't even come close. But this one, the constant approximation is the same as the linear approximation. And so let's write that down. T1 of x, I can actually put it in here. It's equal to that 1, the constant approximation, the 0th degree approximation, plus 0 times x minus 0 is still equal to 1. Okay, so we haven't gotten anything incredibly exciting yet. Not really anything new, of course. Now we go to the quadratic approximation. We need f double prime of x as a function, but only because we're going to be plugging in that 1 base point value. Of course, that's minus cosine x. It's really nice to do this with a function that has simple derivatives, and you get simple patterns. We're going to make a lot of use out of that. So f double prime of 0 is minus 1. Finally, this is going to lead to something new. We get that the second degree, I really shouldn't go down that low. I think my camera has moved a little bit. Let me see if I can squeeze it in here. Yeah, it's not going to be very long. The second degree Taylor polynomial approximation is this 1 plus the 0 part that we got from the first derivative, plus, minus the 1 over 2 minus 1/2, and then here x minus a squared is just going to be x squared. Starting with an example with a equals 0 just for simplicity. This is actually super useful. It says that cosine of x is approximately equal to 1 minus 1/2 x squared, when x is small. And we're going to make that precise because the very next video is going to be about approximation, about the bounds on the remainder. How close can we say this approximation is? How much can we bound the error in that approximation? But just knowing this is a super handy thing. It reduces cosine, which is a fairly complicated gadget to really get values of, and says that roughly it's 1 minus 1/2 x squared. So the picture here is, I don't know where my red pen went. There it is. That I've got a quadratic approximation. That's, of course, not going to capture the wiggliness of cosine. There's no way. But it's not actually horrible. And let me show you a better picture here. This is just taking it out to about 3/4 and minus 3/4 in x. And you can see that the bold line is cosine and the thinner line is 1 minus 1/2 x squared. They're not really that super different. Notice the scale here going 1 to 0.75. It's really quite close. And there's actually a reason why this is closer than it usually would be. And we'll investigate that as we look more at cosine and more at this story. Here's, if you go out further, then you see that it can't really do justice to it. Once cosine starts to curve upward, that's hopeless. We've got a qualitative change. This quadratic approximation, it's a parabola. It's designed to always curve downward. It's always concave down with the same concavity, same second derivative. And this function, the cosine, had a pretty close match on the second derivatives. It's pretty close to a parabola here, but then it decides that it needs to be concave up and start wiggling. Of course, that's not going to work. We'll see that a more complicated approximation will actually start to replicate some of those wiggles, although getting all the wiggles is impossible with a polynomial. Good place to stop this one.